Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Every single star you see when you look up at the night sky it's essentially a survivor.
Oh, absolutely. That is a great way to put it.
Right. Because it is the glowing, burning byproduct of this completely violent, chaotic, and just incredibly destructive factory that likely blew itself to pieces millions of years ago.
Yeah, I think people really lose sight of that.
I want you to just imagine stepping outside your house tonight or, just standing outside on a perfectly clear, crisp, moonless night.
Away from all the city lights, hopefully.
Exactly. You look up, and the canopy is just scattered with these brilliant points of light. And it feels quiet.
It feels very stable, yeah.
Right. It feels serene. But that stability is a profound optical illusion.
It really is. The visible universe is effectively just the exhaust of the system.
The exhaust. I love that.
I mean, it's true. The glowing stars, the things that have captivated human attention for millennia, they represent the absolute final stage of a vastly longer, darker, and infinitely more turbulent process.
So if you only look at the stars,
you're entirely missing the actual story of how the universe builds itself.
Which is exactly why we are completely shifting our perspective today. We are going to plunge into the absolute coldest, darkest, and literally the most massive structures that exist in the cosmos.
The giant molecular clouds, or GMCs.
GMCs, yeah. Our goal here is to figure out the actual mechanics. How does the universe take a vast region of cold, dead, seemingly empty gas and somehow crush it down until it ignites into a burning fusion engine?
And to really understand that, we can't just poke around our own local neighborhood.
Right, we're going big. We're going to look 50 to 60 million light years away at an entire galaxy's worth of these factories just to see the actual blueprints of creation.
Because it is the only way to really understand the fundamental life cycle of a galaxy. I mean, a giant molecular cloud isn't just the birthplace of a single star.
Or even a single cluster of stars, right?
Exactly. The sheer scale, the mass, the mechanics of these structures, they dictate everything about a galaxy. They determine how it changes shape over billions of years, how it, breathes.
And ultimately, what kinds of chemical elements are even available to forge planets.
Yes, and by extension, biology itself.
But the scale is the part that I think breaks the human brain first, because we use the word cloud in everyday life.
Right, you look out the window on a cloudy day.
Exactly. You see these fluffy white collections of water vapor suspended a few miles above your head. But when astrophysicists use the term giant molecular cloud,
they are talking about something so immensely huge that our entire solar system wouldn't even register as a single speck of dust inside it.
A speck of dust.
Yeah.
So before we even get to the specific galaxy we are mapping out, we need to understand the anatomy of the beast. What actually is a GMC?
Well, to define a giant molecular cloud, you have to first look at the baseline environment of space.
Okay, the interstellar medium.
Right. The space between the stars is not an absolute perfect vacuum. It is filled with a highly diffuse mixture of gas and dust.
But out in the open, that gas is relatively warm, right?
Yeah, it's ionized by starlight, and it's spread incredibly thin. But a giant molecular cloud forms when, through a variety of different galactic processes, vast amounts of that gas just get swept up together.
It starts to clump up.
Exactly. Its density increases dramatically, and the sheer volume of it shields the inside from the radiation of the rest of the galaxy.
Like it's building its own shade.
That's a good way to look at it. And because it is shielded, it can finally cool down. And when I say cool down, I mean it reaches temperatures just barely hovering above absolute zero.
Okay, wait, let's put a hard number on that for anyone listening in their car or at the gym right now. Because cold is relative. How cold is this environment?
We are talking about internal temperatures of around 10 to 20 Kelvin.
Which in Fahrenheit is what?
In Fahrenheit, that is roughly minus 440 degrees.
Minus 440 degrees, wow.
Yeah. And to give you some context for that, the ambient background temperature of the entire universe, the leftover heat from the Big Bang itself, is about 2.7 Kelvin.
So these clouds are just a tiny, tiny fraction of a degree warmer than the fundamental floor of physics.
Exactly. Just barely warmer than the background of the universe.
At minus 440 degrees, matter has to behave completely differently, right? I mean, everything just stops.
The atomic behavior changes fundamentally, yes. In the warmer, more diffuse interstellar medium, hydrogen exists mostly as single, unbound atoms just bouncing around.
Because they have too much kinetic energy to stick together.
Right, they just ricochet off each other. But inside these dark, incredibly cold clouds, the hydrogen atoms lose that kinetic energy. They slow down.
They get sluggish.
They get very sluggish. They meet and they bond together to form molecular hydrogen, which is H2. Two hydrogen atoms sharing their electrons.
And that chemical transition is the defining characteristic of these structures, right? That's why we specifically call them molecular clouds.
Precisely. It's all about the molecules.
Okay, so we have this freezing dark pocket of paired up hydrogen. But let's talk size. We throw around astronomical terms a lot, but I really want to ground this. How big is a typical GMC?
A standard giant molecular cloud will span anywhere from tens to hundreds of light years across, or, in the units astronomers actually prefer to use, tens to hundreds of parsecs.
Okay, let's quickly define the parsec, because it's one of those words that sounds like pure science fiction, mostly because of Han Solo, let's be real.
Right, the infamous Kessel Run, which, as a quick aside, was always a unit of distance, not time.
Exactly, take that, Star Wars. But what is a parsec in reality?
In reality, a parsec is simply a unit of distance equivalent to about 3.26 light years. Or roughly 19 trillion miles.
19 trillion miles for one parsec.
Yes. It is derived from a geometric measurement called parallax. That's how astronomers measure the distance to relatively nearby stars by looking at how they shift against the background as the Earth orbits the sun.
Right, like holding your thumb up and closing one eye, then the other.
Exactly that principle, just on a solar system scale. So when an astronomer says a cloud is 30 parsecs across, they mean it is about 100 light years from end to end.
Okay, I want to put 100 light years in perspective for the listener. The distance from our sun to the absolute closest neighboring star, Proxima Centauri, is about 4 light years.
Just over 4, yes.
And the fastest spacecraft humanity has ever built would still take tens of thousands of years to make that single 4 light year trip.
A staggeringly long time.
And you were saying one of these clouds is 100 light years across. I mean, you could stack thousands of our solar systems end to end, and they would just be swallowed up in the dark.
Swallowed up completely. You wouldn't even notice them. And with that kind of physical volume comes an almost incomprehensible amount of mass.
How much mass are we talking?
A typical giant molecular cloud contains the equivalent mass of hundreds of thousands, and sometimes well over 1 million, of our suns.
1 million suns worth of raw material.
Yes. 1 million suns. And while the vast, overwhelming majority of that mass is the molecular hydrogen we just discussed, the cloud is definitely not pure.
It's got some seasoning in it.
A lot of seasoning? It is laced with an incredibly important mixture of other components. Roughly 1% of the cloud's mass is made up of interstellar dust.
When you say dust, you mean like the stuff on my bookshelf?
More like microscopic grains of silicates and carbonaceous material. Think soot and sand, but at a microscopic level.
Okay, soot and sand. Got it.
And then there are trace amounts of other gases, too. Ammonia, carbon monoxide, and even highly complex organic molecules. They are really the ultimate cosmic reservoir.
So we have a reservoir of 1 million suns. It's 100 light years wide. It is full of the exact raw materials needed to build solar systems, and it is hanging right over our heads in our own galaxy, right?
Whoa, absolutely, all over the galaxy.
And in every other galaxy, too. So you would think astronomers could just, point a telescope at the sky and see these massive things literally everywhere.
You would think so.
But that leads to one of the most frustrating paradoxes in astrophysics. These behemoths are practically invisible.
It really is the great irony of star formation. The raw fuel that creates the brightest, most intensely luminous objects in the universe is fundamentally undetectable to standard observational tools.
It's like they're cloaked. Why is that? Right, because it's just two of the exact same hydrogen atoms.
So when it rotates in the freezing cold of a dark cloud, it doesn't emit any easily detectable radiation at all. It is completely silent to our instruments.
It's totally dark. To me, it's like trying to watch a perfectly clear, rushing river at night.
That's a really good analogy.
You know the river is there. You know it spans for miles, and millions of gallons of water are churning and carrying massive amounts of force. But because the water is totally transparent and there is no light bouncing off of it, you stand on the bank and you are just totally blind.
You can't see the currents. You can't map the flow.
Right. So if you are a scientist trying to map that river, you have to get creative. You essentially have to drop a non-toxic fluorescent dye into the water upstream.
Exactly.
You can't see the water itself, but you can track the glowing dye. And by mapping the dye, you map the river.
That river analogy captures the exact methodology of molecular astrophysics perfectly. We literally cannot see the molecular hydrogen water. We are totally blind to the H2.
So we need a cosmic dye.
Yes, we must rely on a tracer. And the most ubiquitous, reliable dye available in these giant molecular clouds is carbon monoxide, CO.
Wait, like the exact same carbon monoxide that comes out of a car exhaust? Or a faulty furnace?
The very same molecule, yes. Now, compared to the vast ocean of hydrogen, carbon monoxide is barely a drop in the bucket. For every single molecule of CO, there are roughly 10,000 molecules of hydrogen.
So it's a very, very faint dye.
Very trace. But carbon monoxide has the one crucial feature that hydrogen lacks. It is asymmetric.
Ah, it's made of one carbon and one oxygen.
Exactly. Oxygen is more electronegative than carbon, which means it pulls the shared electrons slightly toward itself.
It has the imbalance. It has the antenna.
Precisely. Because it has that slight electrical imbalance, the dipole moment when a carbon monoxide molecule gets bumped by a neighboring hydrogen molecule, it starts to spin.
And it hums.
Yes. As it spins, it emits a very specific, very distinct radio frequency. Specifically, it emits at millimeter and submillimeter wavelengths.
Even at minus 440 degrees.
Even at 10 Kelvin, in the absolute freezing depths of the cloud, there is just enough ambient thermal energy from those collisions to keep the carbon monoxide rotating and humming.
So this whole vast invisible cloud of hydrogen is basically singing to us, but we can only hear it through the voice of the trace carbon monoxide.
That's beautifully put, yes. Where you find carbon monoxide emitting these millimeter waves, you are virtually guaranteed to be looking at a dense pocket of molecular hydrogen.
By tuning our instruments to the exact frequency of that CO hum, we can map the entire invisible river.
But as you might guess, there is a catch.
There's always a catch in astrophysics. What is it?
If the dye is glowing specifically in millimeter wavelengths, then pointing a regular telescope at it like the Hubble Space Telescope, which looks primarily at visible and ultraviolet light, is completely useless.
It's like wearing standard sunglasses to look for a specific infrared laser. You just have the wrong lenses.
You have entirely the wrong lenses. If we want to map this massive invisible machinery, we need a machine that is specifically built from the ground up to see millimeter waves.
Which brings us to the Atacama Large Millimeter Submillimeter Array.
ALMA.
ALMA.
Yeah.
Which is, without hyperbole, one of the most phenomenal and, frankly, complex pieces of engineering ever constructed by human hands.
It is the ultimate lens for peering into the dark. It's a marvel.
Let's really dig into LMA, because when you look at pictures of this facility, it honestly looks like a colony on another planet. It does not look like a traditional observatory at all.
No, it doesn't. And it doesn't look like one because it operates on entirely different principles than a standard optical telescope. ALMA is not just a single giant mirror housed inside a shiny silver dome.
Right, it's a sprawling network.
It is an array. It is a network of 66 highly precise individual dish antennas. Most of them are 12 meters across, and they weigh over 100 tons each.
100 tons each, wow.
But the most critical aspect of LMA isn't just the dishes themselves. It is where those dishes are physically located.
Right, the Atacama Desert in northern Chile.
Yeah.
But it's not just the desert. They built this thing at an altitude of 5,000 meters.
Yeah.
Which is over 16,400 feet above sea level. I mean, it is so high up that the engineers and the astronomers who maintain it literally have to carry supplemental oxygen tanks just to avoid hypoxia.
It is a brutally hostile environment for human beings.
So why on earth do you take a multi-billion-dollar, ultra-sensitive international science project and stick it on top of a freezing, oxygen-deprived mountain? I mean, the logistics alone must be a nightmare.
They are, but you do it to escape the Earth's atmosphere. Specifically, you are trying to escape the water vapor.
The humidity.
Exactly. Remember that the carbon monoxide dye we're looking for emits radiation in the millimeter and submillimeter range. It turns out that atmospheric water vapor, the literal humidity in the air that we breathe down here on Earth, is incredibly efficient at absorbing those exact wavelengths.
So it blocks the signal.
Completely. If you built LMA in Florida or even on a standard mountain in California, the moisture in the air would act like an opaque, dense, impenetrable wall.
That's incredibly frustrating to think about.
Right. The faint hum of the carbon monoxide traveling from 50 million light years away would survive its entire cosmic journey across the universe, only to be entirely soaked up by a random rain cloud 2 miles above the telescope.
It would just hit a brick wall at the very last possible second.
Exactly. So you have to get above the water. The Chajnantor Plateau in the Atacama Desert is one of the absolute driest places on the surface of the planet.
And it's 16,400 feet. You're above most of the atmosphere anyway.
Yes, you are sitting above the vast majority of the Earth's atmospheric blanket. The sky up there is exceptionally transparent to millimeter waves. It is truly as close to being in outer space as you can possibly get while still keeping your equipment anchored to the ground.
Okay, so you have 66 massive 100-ton dishes sitting high up in a dry, barren desert. But you mentioned they form an array.
Right.
So they don't just act like 66 separate people looking through 66 separate pairs of binoculars, right? They work as a collective.
They do, and the technique they use to do this is called interferometry. This is where the physics of waves becomes incredibly, incredibly useful.
Okay, how so?
Well, if you want to see highly detailed, sharp structures from millions of light years away, you fundamentally need a massive telescope. The larger the diameter of the dish, the sharper your resolution is going to be.
That makes sense. Bigger lens, better picture.
But physically building a single telescope dish, that is, say, miles across, is structurally impossible. It would simply collapse under its own weight.
Gravity gets in the way.
Exactly. Interferometry is basically the cheat code that gets around this physical limitation.
A cheat code for building a bigger lens. I like that. How does the cheat code work?
By linking multiple smaller dishes together, you can synthesize the aperture of a much larger virtual telescope.
Okay.
When the faint radio wave from the carbon monoxide in a distant galaxy arrives at Earth, it hits one antenna in the array, a tiny microscopic fraction of a picosecond before it hits the next one.
Because they're physically spread out.
Right. The antennas are all connected by miles and miles of fiber optic cables to a specialized supercomputer, which is called a correlator.
The correlator. That sounds very intense.
It is incredibly intense. It is capable of performing quadrillions of operations per second.
Quadrillions?
Wow. Its entire job is to take the signals from all 66 antennas and cross-multiply them, constantly matching up the microscopic delays in the arrival times of the radio waves.
So it stitches them together.
Yes. And by doing this insanely complex math, the array acts as if it were a single colossal telescope whose overall diameter is equal to the distance between the two furthest antennas in the network.
And the antennas aren't bolted to the ground permanently, are they?
No, they aren't.
Because I've seen footage of these massive custom-built tractor vehicles that literally drive up to a 100-ton antenna, pick the whole thing up, and drive it across the desert to a new concrete pad.
Yes, those are the ALMA transporters. They're named Otto and Lore. They allow the entire array to be constantly reconfigured.
So you can zoom in and out.
Exactly. If astronomers want a wide-field, zoomed-out view of the sky, they use the transporters to cluster all the antennas closely together. But if they want maximum sharpness, the ultimate zoom, they use the transporters to physically spread the antennas out across the desert plateau.
How far apart?
They can extend the baseline up to 16 kilometers across.
16 kilometers.
Yeah.
So you are literally computationally building a telescope the size of a major city just to stare deep into space.
Yes. And the result of that city-sized virtual dish is unprecedented angular resolution. When spread out, LMA can resolve details down to a fraction of an arcsecond.
Okay, let's ground that. What does a fraction of an arcsecond actually look like?
Imagine standing in New York City, looking through a telescope, and being able to clearly distinguish the individual dimples on a golf ball sitting on a tee in Los Angeles.
You are kidding.
No, that is the level of pinpoint sharpness we are talking about.
From New York to LA, that is insane.
It is, and we absolutely need that sharpness, because to see the fine internal structure of a giant molecular cloud that is only a few dozen parsecs across and located inside a galaxy tens of millions of light years away, you need the ultimate magnifying glass.
And crucially, because LMA is looking at radio waves, it doesn't care about the dust at all, right?
Not even a little bit.
Because if you point a normal optical telescope at a star-forming region, all you see is a giant black smudge. The interstellar dust grains just physically block the visible light from the stars forming inside.
Yes, optical telescopes are completely blind to the interior, but millimeter waves just slip right around those dust grains. ALMA cuts right through the cosmic smog.
It pierces the veil entirely.
It does. But honestly, the most powerful aspect of LMA isn't just that it takes a clear picture, it is that it takes a moving picture.
What do you mean, like a video?
Sort of. By observing the specific frequency of the carbon monoxide, ALMA is essentially measuring a Doppler shift.
Okay, like a police siren changing pitch as it drives past you on the highway.
Exactly the same principle, but with light instead of sound. If a pocket of gas inside the giant molecular cloud is moving toward Earth, the millimeter waves of the carbon monoxide get compressed, shifting to a slightly higher frequency.
A blue shift.
Right. And if the gas is churning away from Earth, the waves stretch out to a lower frequency, a red shift.
And ALMA can detect that.
ALMA is so precise that it can map these minute frequency shifts across the entire cloud simultaneously, so it doesn't just see a static blob of gas.
It maps the internal kinematics.
Yes. It reads the velocity, the turbulence, and the temperature of the gas in real time. It actually shows us how the machinery inside the factory is moving.
Okay, so we have the ultimate tool. We have a city-sized robotic supercomputing telescope array perched on top of the driest mountain in the world, specifically designed to read the speed and temperature of invisible gas by tracking trace amounts of glowing carbon monoxide.
That's the summary, yes.
Now comes the obvious logistical question.
Yeah.
You have this incredible machine. Where do you point it?
Ah, yes. The targeting question.
Because the instinct for anyone would be to say, well, we live in the Milky Way. Our galaxy has spiral arms completely full of giant molecular clouds. Why not just look in our own backyard?
And for decades, that is exactly what astronomers did. We have intensely studied the local star-forming regions.
Like the Orion Nebula.
Exactly. Regions like the Orion Molecular Cloud Complex, which is only about 1,300 light-years away, or the Taurus Molecular Cloud, or even the incredibly dense, chaotic Central Molecular Zone, right at our galactic core.
So we have looked close to home.
We have, and we have learned an immense amount from them. But studying the Milky Way from inside the Milky Way comes with a fatal flaw. Astronomers refer to it as the line of sight problem.
The line of sight problem. Okay.
Okay.
I try to picture it like this. Imagine standing in the middle of a massive, incredibly dense, old-growth forest.
Okay.
You have no pad, and your job is to map exactly where every single tree is and how big it is. You look directly north. You see a massive oak tree right in front of you. You write it down. But what you absolutely cannot see is whether there are 5 more oak trees lined up perfectly behind that first one. The trunk in the foreground completely blocks the background.
That is the perfect visualization of the problem.
Because our solar system is embedded deep inside the flat disk of the Milky Way, right? So when we look out into the galactic plane, we're just looking through the forest. We see everything squished and projected onto a single two-dimensional slice of the sky.
Yes. If you see a massive emission of carbon monoxide in the Milky Way, it is incredibly difficult to know if you are looking at one single, colossal, giant molecular cloud, or if you are looking at 3 smaller, distinct clouds that just happen to lie along the exact same line of sight.
Just separated by thousands of light years of empty space behind each other.
Exactly. You have the velocity data from the Doppler shift, which helps untangle it a bit, but distance ambiguities just constantly plague galactic astronomy.
It's just a mess of overlapping data.
It makes it incredibly difficult to get clean, isolated, true 3-dimensional properties of the clouds. And more importantly, you can't get reliable population statistics across the whole galaxy because you can never see the whole galaxy at once.
You are forever stuck in the middle of the trees.
You are.
So if you want a perfect map of the forest, you have to leave it. And since we obviously cannot physically fly a spaceship outside the Milky Way to look back down at it, we have to find a completely different forest to look at. A forest that we can view from a completely different angle.
Which leads the researchers to target the galaxy NGC 1387.
Let's set the stage with NGC 1387. Where are we looking, and why is this specific galaxy the holy grail for this kind of mapping?
NGC 1387 is located in the constellation Fornax. It sits roughly 50 to 60 million light-years away from Earth.
60 million light-years. That is quite the jump from our local neighborhood.
It is, but structurally, it is a barred spiral galaxy, somewhat similar to our own Milky Way. It has a central structure, a bar, and an extended disk.
But what makes it so special?
The absolute defining characteristic that makes NGC 1387 so incredibly valuable is its inclination angle relative to Earth. We view it almost entirely face-on.
Oh, wow. So instead of looking at the galaxy edge-on, where it would just look like a thin, bright line cutting across the sky, which would obviously give us the exact same line of sight problem we have, here we are essentially hovering above it.
Exactly. We are looking down at the face of a clock.
That is perfect.
Yes. The face-on top-down perspective entirely strips away the ambiguity. When LMA points at the disk of NGC 1387 and detects a giant molecular cloud, we know exactly where it is.
Because there's nothing behind it to get confused with.
Right. We know its exact distance from the center of that galaxy. We know we are seeing its true isolated boundaries without 5 other clouds photobombing it in the foreground or background.
So it's a completely clean data set.
It allows astronomers to conduct a pure, uncontaminated census of an entire galactic ecosystem with all the clouds situated at a known uniform distance from our telescope.
Okay, so the team takes ALMA, they point it at Fornax, and they stare down at the face of NGC 1387. They tune the receivers to catch the carbon monoxide hum. What did they actually catch in the net?
They brought back an absolute treasure trove of data. The survey resulted in the rigorous identification of 1,285 distinct individual giant molecular clouds scattered across the rotating gas disk of NGC 1387.
1,285. That is mind-boggling.
It really is a staggering number.
I mean, they didn't just find a few interesting case studies to write a paper on. They cataloged an entire population. They essentially mapped the entire industrial sector of a foreign galaxy.
The word unprecedented gets overused in science a lot, but in this case, it absolutely applies. To have a highly resolved, uniform, kinematic map of nearly 1,300 distinct star-forming factories in a single external galaxy represents a massive leap in capability.
It changes the game entirely.
It really does. We are moving from studying individual anecdotes to doing hard, rigorous population statistics. We can finally ask, what does a normal molecular cloud actually look like?
So let's look at the stats. You have 12,285 clouds on a spreadsheet. What happens when you start analyzing their physical properties?
Well, let's start with their physical footprints. Across the entire population, the mean radius of a cloud is roughly 20 parsecs, or about 65 light years.
Okay, 65 light years on average.
But averages can be very deceiving. The distribution includes massive outliers, the true giants, the colossal complexes within the spiral structure boast radii exceeding 100 to 150 light years.
And the masses of these structures, because we said 1 million suns earlier.
They are equally staggering. The masses range from tens of thousands of solar masses at the small, diffuse end, all the way up to well over 1 million solar masses for the largest, most gravitationally dominant complexes.
But the real insight comes when you look at how those masses are distributed across the population, right?
Yes, exactly. Because the universe rarely just throws things out randomly.
There's usually a pattern.
Always. When astronomers plot the number of clouds on a graph against their respective masses, they don't just see a random bell curve. They see a very strict mathematical relationship known as a truncated power law.
A truncated power law.
Specifically, for NGC 1387, the slope of this power law falls between minus 1.7 and minus 1.8.
Okay, I want to pause and dissect this, because truncated power law with a slope of minus 1.7 sounds intensely like a math exam.
It does sound a bit dry.
But I know there is deep physical meaning hidden in that phrase. Let's translate it. If I'm understanding this correctly, a power law basically dictates a ratio of big things to small things.
That's a good way to frame it.
So it means you're going to have an enormous number of very small clouds, a moderate number of medium clouds, and a tiny, incredibly rare handful of absolute behemoths. It is a strict hierarchy.
Yes.
And the slope that minus 1.7 is the mathematical rule that tells you exactly how much rarer a cloud becomes as you scale up the mass.
That is a perfect translation. The power law describes the scale-free nature of the gas. But the truly fascinating part is why the gas organizes itself according to this specific slope.
Why does it? Does minus 1.7 mean something specific?
It does. A slope hovering around minus 1.7 to minus 2.0 is a very well-known mathematical signature in physics. It is the signature of fractal supersonic turbulence.
Fractal turbulence. Let's unpack that. When people hear fractal, they usually think of those trippy, zooming computer graphics where a shape perfectly repeats itself no matter how far you zoom in.
Right, the Mandelbrot sets.
Or like the branching of a tree or the veins on a fern leaf.
Exactly. A giant molecular cloud is not just a smooth, uniform balloon filled with hydrogen gas. It is a highly complex, fractal environment shaped by opposing forces.
The tug of war.
Yes. You have the immense gravity of 1 million suns trying to crush the cloud inward. But fighting against that gravity is the internal kinetic energy, the turbulence.
The gas is moving.
The gas inside the cloud is churning and roiling at supersonic speeds. This turbulence creates a fractal structure of shocks and eddies. Big turbulent flows break down into smaller turbulent flows, which break down into even smaller turbulent flows.
Just like the zooming graphic.
Exactly. This physical cascade of energy naturally partitions the gas, creating a lot of small clumps and very few large ones, resulting in that exact minus 1.7 mathematical slope.
So the math is just a mirror reflecting the fluid dynamics of space. That is just beautiful.
It really is elegant.
But you also mentioned the power law was truncated. What does truncated mean in this context?
Well, a standard power law would technically go on forever. You would just keep getting bigger and rarer clouds infinitely. But physics sets hard limits.
The universe has rules.
The truncation point is the upper mass limit. It is the point on the graph where the line suddenly plummets to zero.
Meaning no clouds exist past that size.
Right. It tells us that a giant molecular cloud cannot grow to 10 million or 100 million solar masses. At a certain point, a cloud simply becomes too physically large for its own gravity to hold it together against the shearing forces of the rotating galaxy.
The galaxy just rips it apart if it gets too greedy.
Exactly. The truncation point is essentially the galaxy saying, this is the maximum allowable size for a star factory, no bigger.
So we have the outside boundaries, we have the mass limits. But what happens when you use LMA's incredible resolution to actually zoom in past the boundary and look at the internal architecture of one of these specific clouds? What is the actual ecosystem inside?
It is a deeply structured hierarchy. If you peer deep into the interior of the cloud, bypassing the diffuse outer layers, you find what astronomers call the dense cores.
The dense cores.
These are the hearts of the factory. In these specific regions, the density of the gas spikes dramatically, reaching thousands or even tens of thousands of molecules per cubic centimeter.
Okay, I need to interject with some terrestrial perspective here, because hearing thousands of molecules per cubic centimeter sounds incredibly dense, like a solid brick of gas.
Right, it sounds packed.
But compared to the air on Earth, it is absolutely nothing, right?
By terrestrial standards, a dense molecular core is a vacuum harder than anything an Earth-based laboratory could ever dream of engineering.
Put it in perspective for us.
The air in the room you are sitting in right now contains roughly 10 quintillion molecules per cubic centimeter.
10 quintillion.
A giant molecular cloud core has 10,000. It is incomprehensibly sparse to us.
But by the standards of outer space, it's a cosmic traffic jam.
Exactly. And that relative density is all that matters. Because when the gas gets that crowded relative to its surroundings, it can finally shield itself entirely from any external heat. It cools to the absolute minimum.
And when it gets that cold,
With the heat and outward pressure basically gone, gravity finally wins the tug of war. The core begins to collapse inward. These dense cores are the literal wombs. They are the exact localized sites where gravitational collapse becomes imminent, leading to the birth of a protostar.
but a core can't just sustain itself in a vacuum, right? It needs to pull material from the rest of the cloud. ALMA also revealed the plumbing system, didn't it?
Yes, it did. Connecting these dense cores to the vast, wider body of the cloud are filamentary structures.
Filaments, what do they look like?
They are literal rivers of gas. The ALMA data clearly shows these elongated threads routing material through the cloud. The supersonic turbulence we discussed earlier compresses the gas into these filaments, and gravity acts as the pump.
Channeling the material.
Yes, channeling material down the filaments to constantly feed the dense cores. And surrounding this entire network of rivers and cores is the diffuse envelope, a vast lower density halo that acts as the transition zone between the freezing molecular cloud and the warmer atomic gas of the galaxy.
So, looking at NGC 1387, we have just outlined a master blueprint. 1,285 clouds. We know the mass ratios, the fractal turbulent structure, the dense cores, the filamentary plumbing. We essentially have the exact specs of the factory.
We do. It's a complete structural breakdown.
So now we can take this massive data set and point it at one of the most profound, overarching questions in astrophysics. It's something that scientists have debated for decades.
Universality.
Yes. Are the rules of star formation universal? Does physics care where it is?
That is a big question.
If I take 1 million solar masses of molecular hydrogen and drop it in the chaotic center of the Milky Way, will it behave exactly the same way as 1 million solar masses of hydrogen floating 50 million light years away in the quiet suburbs of Fornax?
That is the ultimate test. We want to know if the recipe for a star is an immutable law of nature, or if it changes fundamentally based on the local neighborhood.
And to test this hypothesis, astrophysicists rely on a historical framework known as Larson's laws.
Larson's laws, yes.
Let's go back into the history of astronomy for a second to explain these. Where did they come from?
In 1981, an astrophysicist named Richard Larson published a seminal paper. He had been studying the relatively small sample of molecular clouds that we could actually observe inside the Milky Way at the time.
Through all the trees.
Exactly, working through the line of sight issues. But through his observations, he noticed three distinct scaling relationships that seemed to govern how these clouds behaved.
What were the three relationships?
The first law states that there is a strict relationship between a cloud's physical size and its internal velocity dispersion.
Okay, velocity dispersion. That's simply a measure of how violently the gas inside the cloud is churning and moving, right?
Yes. Larson realized that larger clouds have intrinsically higher velocity dispersions. The bigger the cloud, the faster and more violently the gas inside it is swirling.
Makes sense. More mass, more gravity, more turbulence. What about the second law?
The second law relates a cloud's size to its total mass, effectively demonstrating that clouds have a roughly uniform column density regardless of their overall volume.
Okay. And the third law?
The third law relates to the balance of energies, specifically something called the virial theorem.
The virial theorem. I remember you mentioning this earlier when talking about the tug of war in the cloud. Let's go that down so it's not just a jargon term.
Absolutely. The virial parameter is essentially a ratio. It is a way of comparing the kinetic energy of the cloud, the turbulence, the outward pressure trying to blow the cloud apart against the gravitational potential energy.
Which is the inward pull trying to crush the cloud into a star.
Exactly.
Yep.
If a cloud is in what we call virial equilibrium, those two forces are perfectly balanced. The cloud neither collapses nor expands. It just hangs there in a stable, steady state.
It's just chilling.
Right. And Larson observed that most molecular clouds in the Milky Way seem to hover near this state of virial equilibrium.
Okay, so Larson establishes these laws in 1981 using the Milky Way. Fast forward 40-something years, you have this pristine, massive new data set of 12,285 clouds from a completely different galaxy, 60 million light years away.
A totally fresh data set.
You apply Larson's laws to the Fornax clouds. What does the math show?
Astoundingly, the clouds in NGC 1387 fall perfectly in line. Perfectly. When the research team plotted the size, mass, and velocity dispersion of the 12,285 clouds, the data points traced the exact same scaling relationships that Larson found in the Milky Way.
Wow.
The physics mapped cleanly across tens of millions of light years.
Which provides massive support for the idea that the universe really just has one single universal recipe for building a star factory.
It does. It heavily implies that the core physics, the way a gas cloud supports itself against gravity via internal fractal turbulence, and the way it ultimately fragments to build dense cores, is governed by fundamental thermodynamic and gravitational constants.
The basic machinery is identical everywhere.
Exactly the same.
But I am going to push back on this just a little bit, because my instinct tells me that can't be the whole story.
So please do push back.
If star formation is a perfectly universal, unbreakable law, then the local environment doesn't matter at all. That feels wrong to me.
Why does it feel wrong?
You are telling me that a molecular cloud sitting near the chaotic, radiation-soaked, hyperdense core of a galaxy operates perfectly identically to a cloud floating out in the quiet, empty, dark outer suburbs of a spiral arm. The neighborhood has to exert some influence.
Your instinct is spot on, and that exact tension is what makes modern astrophysics so vibrant. The statement that star formation is universal is true in the broad strokes, but it is incomplete.
The devil is in the details.
Always. And this is exactly why having a sample size of 12,285 clouds is so absolutely critical. When you have a data set that massive, you aren't just looking at the average trend line anymore. You can finally observe the statistical deviations.
The outlier.
You can see the subtle tweaks. And those subtle deviations prove that the galactic environment absolutely does matter.
Okay, so the core engine is the same, but the local environment applies the tuning. What kind of environmental tweaks are we talking about here? How does the galaxy mess with the cloud?
The most prominent environmental factor is galactic shear.
Galactic shear.
Think about how a galaxy rotates. It isn't a solid dinner plate spinning on a stick. The inner parts of the galaxy orbit much faster than the outer parts.
Right, because they're closer to the center of mass.
Exactly. So if you have a giant molecular cloud that spans 150 light years across, and it is located somewhat near the galactic center, the gravitational pull on the side of the cloud closest to the core is significantly stronger than the pull on the far side of the cloud.
Because the inner edge is physically closer to the supermassive black hole and all the dense stars.
Exactly. This differential gravity, the shear force, physically pulls on the cloud. It stretches it, It actively elongates the gas, pulling it out of a spherical shape into a smeared oval.
So it's like stretching taffy.
Yes, and it can also induce massive violent rotation into the cloud structure itself.
So the galaxy is literally kneading the cloud like bread dough.
It is. And the deep galactic potential, the overall gravitational field of the galaxy's center, can drive external energy directly into the cloud. This forces the internal velocity dispersion we talked about to spike wildly.
It makes it more turbulent.
Much more. The ALMA data from NGC 1387 specifically highlights regions exhibiting extreme supersonic line widths.
Okay, let's clarify supersonic line widths. We touched on this briefly, but it means the gas inside the cloud is literally moving faster than the speed of sound.
Yes.
Now, on Earth, at sea level, the speed of sound is about 760 miles per hour. But I assume the speed of sound in a molecular cloud at minus 440 degrees Fahrenheit is vastly different.
It is vastly slower. In a 10 Kelvin molecular gas, the speed of sound is only a fraction of a kilometer per second.
Okay, so it's a very low bar to cross.
But the gas inside these clouds is churning at several kilometers per second. It is perpetually, constantly breaking the sound barrier.
So the inside of this cloud is just a continuous, violent network of sonic booms. It's a chaotic storm of shockwaves just crashing into each other over and over.
It is absolute chaos, yes. But it is a highly productive chaos.
Productive how?
Remember the filamentary rivers we discussed?
The plumbing.
Those filaments are physically carved out by these intersecting supersonic shockwaves. When two shockwaves collide, they violently compress the gas between them, creating a dense, thread-like river.
So the shockwaves build the rivers.
This filamentary accretion is the cosmic plumbing system in action. The severe turbulence actually acts as a support mechanism, preventing the entire million solar mass cloud from collapsing all at once in a catastrophic freefall, while simultaneously forcing gas down the narrow filaments to feed the dense cores.
Okay, let's just step back for a second and look at the picture we've painted here.
Yeah.
Because it's a lot.
It's a very complex system.
You have a massive structure, 100 light years across. It possesses the gravity of 1 million suns. It has highly organized, dense cores acting as literal wombs. It has supersonic shock waves carving out rivers to efficiently funnel raw fuel directly into the ignition zones.
Right.
When you describe the mechanics like that, a giant molecular cloud sounds like the most ruthlessly efficient factory ever conceived. You would expect it to just rapidly convert all of that million solar mass gas into 1 million stars in a brilliant flash of cosmic productivity.
You would certainly expect that.
But the reality is the exact opposite, isn't it?
This is one of the most counterintuitive and arguably the most crucial facts about galactic evolution. Starbirth is staggeringly inefficient.
Despite millions of solar masses of raw fuel.
Despite gravity working tirelessly to crush it all together, yes, the factory is, by most metrics, a failure.
How much of a failure? If I have a cloud with 1 million solar masses of pristine hydrogen gas, how many solar masses actually become stars?
The standard metric across astrophysics, which the NGC 1387 data strongly supports, is the 1 to 10% rule.
Wait. 1 to 10%.
Of the total initial mass of a giant molecular cloud, only about 1% to 10% actually successfully condenses to form a star.
That is the ultimate aha paradox to me. You have the perfect factory. You have 1 million tons of raw material ready to go on the assembly line. And before the shift is over, 90% to 99% of the raw material is just thrown out the window into the void.
Unused.
It doesn't get used. Why? What on earth is powerful enough to stop 1 million suns worth of gravity from finishing the job?
The only thing powerful enough to stop a star factory is a star.
Okay, now that sounds like poetry.
It's physics. The phenomenon is called stellar feedback.
Stellar feedback. Let's delve deep into the destruction of the cloud. How do the stars destroy their own cradle?
It primarily comes down to timing and mass. When a cloud begins to fragment and collapse, it does not create 1 million identical stars all at exactly the same time.
It's not perfectly synchronized.
The mass of the newly born stars follows a distribution called the initial mass function. This function dictates that while the cloud will create thousands of tiny, dim, red dwarf stars, it will also create a tiny handful of absolute monsters.
The heavyweights of the universe.
The O-type and early B-type stars. These stars are tens or even hundreds of times more massive than our sun.
And because they are so massive,
their core temperatures are unimaginably hot. The moment nuclear fusion ignites in the core of an O-type star, it unleashes a cataclysmic torrent of energy directly into the surrounding cloud.
So the moment the factory turns on, The machinery immediately starts melting.
Literally melting. The first phase of destruction is radiation. These massive stars emit blistering, lethal levels of ultraviolet radiation.
UV light.
This UV light slams into the freezing cold molecular hydrogen that surrounds the star. The radiation is so intense that it physically strips the electrons off the hydrogen molecules, dissociating the H2 back into single atoms and then completely ionizing them.
Oh, wow. It unmakes the molecules.
Yes. This creates a rapidly expanding bubble of superheated plasma called an HII region. The freezing 10 Kelvin gas is suddenly flash heated to 10,000 Kelvin.
So the baby stars are literally vaporizing their own food source.
They absolutely are, but the UV radiation is just the opening act of the destruction.
There's more.
Oh, yes. These massive stars also generate ferocious stellar winds.
Like solar winds, but bigger.
Much bigger. These are continuous streams of charged particles blowing off the star's surface at millions of miles per hour. These winds act like a cosmic hurricane, physically slamming into the dense gas of the cloud and violently pushing it outward, physically clearing out the factory floor.
Just sweeping the gas away. And because these supermassive O-type stars burn so hot, they burn through their nuclear fuel incredibly fast, right? They don't live for billions of years like our sun.
Not at all. They live fast and die young. An O-type star might only live for 3 to 5 million years.
In galactic terms, that is literally the blink of an eye.
It is nothing, and when they run out of fuel, they do not go quietly. They die in spectacularly violent supernova explosions.
And that's the finale.
The shock wave from a supernova travels outward at thousands of kilometers per second. When that shock wave hits the remaining structure of the giant molecular cloud, it is the final death blow.
The blast physically rips the cloud apart,
violently ejecting the remaining 90% of the unconsumed pristine molecular gas back out into the interstellar medium.
The cradle is just completely shattered. The factory is permanently shut down before it could even finish processing its raw inventory. That is just an incredibly poetic but violent image.
It is the brutal reality of star formation.
And I imagine that having this exhaustive catalog of 285 clouds from NGC 1387 gives astrophysicists the exact tool they need to study this battle between gravity and stellar feedback, right?
It serves as the ultimate forensic laboratory, because we now have a comprehensive map of all the gas clouds in the galaxy, and we can also use optical telescopes to see exactly where the young, brightly growing stellar clusters are. We can match them up.
Oh, you can overlay the map.
Exactly. Astronomers can look at a specific cloud, measure its mass, its surface density, and its virial parameter with ALMA, and then look with an optical telescope to see if a star cluster has ignited inside it yet.
So you can see the before, during, and after.
By looking at hundreds of these regions at various stages of their life cycle, researchers can essentially watch a time-lapse of the destruction. They can test incredibly complex theoretical models to see exactly how many million years it takes for a cluster of massive stars to entirely disassemble a giant molecular cloud.
Okay, so the massive stars throw a tantrum, they go supernova, and they blast 90% of the cloud's gas back out into the void.
Right.
But that gas doesn't just disappear. The factory is destroyed, but the raw material survives. It gets pushed somewhere else. It feels like this is the exact moment we really need to zoom out from the individual cloud and look at the macro picture. How does this endless cycle impact the entire galaxy?
Zooming out is absolutely essential here because giant molecular clouds are not just isolated local phenomena that live and die without consequence. They are the primary engines of evolution for the entire galaxy.
The engines of evolution.
You can accurately think of the total molecular gas reservoir as the fuel gauge for a galaxy's lifespan.
The fuel gauge. So as long as there is molecular gas, the galaxy is alive.
Yes. The availability of this gas, how it is distributed across the spiral arms, and crucially the rate at which it is consumed and destroyed, totally dictates the morphological evolution of the galaxy over billions of years.
It dictates its shape.
Its shape, its brightness, everything. It also dictates the entire history of its chemical enrichment.
Let's really focus on that chemical enrichment for a second, because this is where the cosmic recycling program comes in. The phrase astronomers use is metallicity, right?
Yes, metallicity.
Which is deeply confusing to lay people,
Yeah.
because to an astronomer, literally anything heavier than helium is considered a metal.
It's a very old quirk of astronomical terminology, I admit, but the concept is crucial. During the Big Bang, the universe essentially only produced hydrogen and a bit of helium.
Nothing else.
Nothing else. Every single heavier element, carbon, oxygen, nitrogen, iron, silicon, every single one of them had to be forged later. inside the burning cores of massive stars.
So when that O-type star we just talked about reaches the end of its life and explodes in a supernova, it doesn't just blow away the original hydrogen cloud.
No, it violently ejects all of those newly forged heavy elements out into the interstellar medium along with the gas.
It seeds the galaxy with the good stuff.
Exactly. That newly enriched gas, now carrying traces of carbon and oxygen, drifts through the galaxy. Eventually, over millions of years, it gets swept up again, cools down, and forms a brand new giant molecular cloud.
But this new cloud has a slightly higher metallicity than the one before it.
Right, it has more trace elements, and the next generation of stars that form from this cloud will have more heavy elements built into them. It is an endless billion-year cycle of cosmic recycling, slowly enriching the galaxy, generation after generation.
And the physical shape of the galaxy plays a massive role in how this gas is moved around and recycled, right?
The shape is incredibly important.
Let's go back to NGC 1387. We mentioned at the very beginning that it is a barred spiral. Our Milky Way is also a barred spiral. Let's explain what that bar actually does to the gas. It isn't just a static, pretty shape in the center of the galaxy, is it?
Not at all. The central bar of a galaxy, which is a dense, elongated structure of older stars cutting right through the galactic core, is a highly dynamic physical funnel.
A funnel.
The physics of how gas orbits within a galaxy are complex. In a normal unbarred spiral disk, gas clouds orbit in relatively stable, mostly circular paths, but the intense asymmetrical gravitational field of the central bar acts like a brake.
It disrupts the orbit.
It creates torques that actively rob the giant molecular clouds of their angular momentum.
Meaning the clouds can no longer maintain their stable circular orbits.
Precisely. Because they lose their orbital momentum, the gas clouds are literally forced to migrate. They funnel steadily inward, sliding down the gravitational well toward the absolute center of the galaxy.
So the bar is literally a conveyor belt, relentlessly dumping millions of solar masses of cold gas directly into the galactic core. What happens when all that gas piles up in the center?
The results are spectacular. The immense concentration of molecular gas in the central region can trigger violent, massive bursts of star formation, completely changing the luminosity of the galactic core.
It lights up.
It lights up tremendously. But more profoundly, if the galaxy hosts a supermassive black hole at its absolute center, this bar-driven funneling of molecular clouds is exactly the mechanism required to feed it.
Because the black hole needs fuel, too.
Yes. When the black hole consumes this gas, it unleashes staggering amounts of energy, transforming the core into an active galactic nucleus, or AGN. The radiation from an AGN can be so intense that it outshines the rest of the galaxy combined.
So by mapping the kinematics of the clouds in NGC 1387, we are literally watching the physical mechanism that dictates whether a supermassive black hole starves or feeds.
We are watching the feeding tube.
It is just incredible how interconnected it all is. A cloud forms, it makes stars, the stars blow it up, the bar funnels the remnants to the black hole. But there is another layer to this entirely. You mentioned earlier that mapping these relatively local galaxies, like Fornax at 60 million light-years, is essential for a completely different field of astronomy.
Yes, cosmology.
It helps us look at the dawn of time.
Yeah.
How does studying a modern factory help us understand the early universe?
It acts as a totally necessary calibration tool. Right now, modern astronomy is obsessed with pushing our observational boundaries as far back as physically possible.
We want to see the beginning.
We want to see the epoch of reionization. We want to look back over 13 billion years and see the very first primordial galaxies forming out of the dark ages of the early universe.
And we are building insane new machines to do this.
Yes, mega facilities are coming online in the coming decades, like the next generation very large array, the NGVLA, or the Square Kilometer Array, the SK. These arrays will be vast, spanning entire continents.
Continent-sized telescopes. It's wild.
But there is a fundamental limit to observation. When these future super telescopes capture a radio signal from a galaxy that is 13 billion light-years away, that signal is going to be incredibly faint, and the spatial resolution will be poor.
Because it's so unimaginably far away. Even with a telescope the size of a continent, the early galaxy is just going to look like a few blurry pixels of data on a screen.
Exactly. They will not be able to see the fine details. They won't see individual giant molecular clouds like we do in Fornax. They will just see a faint, generalized smudge of carbon monoxide emission.
So if it's just a smudge, the critical question for an astronomer is, How do you know what physical processes are actually happening inside that blurry smudge?
Right, you need a decoder ring.
A decoder ring.
You need a gold standard template, and that is exactly what the NGC 1387 dataset provides. By exhaustively mapping the 12,285 clouds in our local universe at high resolution, we understand the exact mechanics.
We know how it works locally.
We know exactly how the total gas mass correlates to the rate of star formation. We know how the internal velocity dispersion behaves. So when future astronomers look at that blurry smudge from the dawn of time, they will apply the mechanical rules we learned from NGC 1387.
Wow.
They will extrapolate our local high-fidelity knowledge to interpret the physics of the primordial universe.
That is a brilliantly practical scientific strategy. We basically spend years perfectly mapping out the mechanics of the engine sitting in our neighbor's driveway. We learn every valve, every piston, so that when we see a blurry engine racing on the other side of the planet through a pair of binoculars, we already know exactly how it works inside.
That is exactly what we're doing.
But before we crown LMA as the flawless, omniscient god of astronomy, we really have to talk about the blind spots. Because as perfect as this 12,285 cloud dataset seems, the methodology actually has a glaring flaw. LMA doesn't see everything.
That is a vital caveat, and it is something astronomers have to rigorously mathematically account for. No instrument in existence is perfect, and interferometers, like LMA, suffer from a very specific structural blind spot.
It fundamentally comes down to how the mathematics of synthesizing a virtual telescope works, doesn't it?
It does. It goes back to the baselines. The physical distance between the 66 antenna dishes sitting out in the desert.
Explain that.
Because LMA uses the distance between its antennas to achieve its razor-sharp, ultra-high resolution, the instrument is highly optimized to detect small, distinct, high-contrast structures.
They like sharp edges.
Yes. It is phenomenally good at seeing the dense molecular cores and the sharp filamentary rivers. But the mathematical process of cross-correlating the signals essentially acts as a spatial filter in the Fourier plane.
Okay, let's break that down with an analogy. Because Fourier planes can get incredibly dense for people.
Please do.
Imagine you have a highly specialized, perfectly focused macro camera lens.
Yeah.
You point it at a massive oak tree. The lens is so specifically designed to capture fine detail that it takes a flawless, incredibly sharp picture of the individual veins on a single leaf.
Right.
But because it is so hyper-focused on the sharp edges, it physically cannot record the massive, smooth, vast blue sky sitting directly behind the leaf. The sky has no sharp contrast, so the lens just zeroes it out. The sky becomes invisible in the data.
That is a highly accurate way to visualize it. In radio astronomy, this is known as the missing flux problem.
Missing flux.
Giant molecular clouds do not just exist in a vacuum. They are often surrounded by and embedded within vast, smoothly distributed, highly diffuse envelopes of gas that span across the galactic arms.
And ALMA misses it.
Because this gas is smooth and lacks sharp contrast, ALMA's high-resolution array simply filters it out. It doesn't see it.
Which means if you just look at the ALMA data alone, you might be missing a massive chunk of the galaxy's total fuel supply.
You absolutely are. A significant percentage of the total molecular gas in NGC 1387 might not be locked up in the dense, easily visible GMCs. It might be out in that diffuse, invisible component.
So how do you fix that?
To capture that missing piece of the puzzle and to get the true total gas mass of the galaxy, astronomers cannot rely on LMA alone. They have to combine LMA's high-resolution maps with separate observations from large single-dish telescopes.
Because a single dish works differently.
A single-dish telescope doesn't have the sharpness to see the cores, but it is excellent at measuring the total broad-brush brightness of the diffuse sky. By merging the two data sets, you finally get the complete picture.
So there is still heavy lifting to do just to count the basic gas mass.
Mm-hmm.
But there is another frontier here that we only briefly touched on at the very beginning of the show. And I really want to dive deep into it because it borders on astrobiology.
The chemistry.
The chemistry. We mentioned that these clouds are mostly hydrogen with a trace of carbon monoxide dye. But there are other things hiding in the dark. Complex organic molecules, COMs.
Yes, and this is arguably one of the most exciting and rapidly expanding fields in modern astrophysics, astrochemistry. It turns out that giant molecular clouds are not just cold storage units, they are highly active chemical laboratories.
But wait, how? We just established that the core of the cloud is 10 Kelvin. It is minus 440 degrees. At that temperature, chemical reactions should basically be frozen solid. There's no heat to drive the chemistry.
That was the assumption for a very long time. Gas phase chemistry, where two atoms bump into each other in the void and bond, is incredibly slow at these temperatures.
Right.
But the key is the dust. Remember the microscopic grains of silicate and carbon soot we mentioned earlier?
The 1% of the cloud.
Yes. These dust grains are the secret catalysts.
How does dust change the chemistry in a freezing cloud?
In the freezing depths of the cloud, stray atoms of oxygen, carbon, and nitrogen drift around until they collide with a grain of dust. When they hit the dust, they stick to it.
They freeze to the surface.
Over thousands of years, the dust grain becomes coated in a microscopic mantle of ice. And not just water ice, but frozen ammonia, frozen methane, and frozen carbon monoxide.
It's like a tiny snowball of chemicals.
The surface of the dust grain acts as a tiny workbench. The atoms are trapped closely together on the surface, allowing them to interact and form much more complex bonds.
But they still need energy to react, don't they? Where does the spark come from if there are no stars yet?
The energy comes from cosmic rays.
Cosmic rays.
These are high-energy protons zipping through the galaxy at nearly the speed of light. They penetrate deep into the dark cloud and slam directly into the ice mantles on the dust grains.
Like tiny bullets.
Exactly. The impact of a cosmic ray shatters the simple molecules in the ice, creating highly reactive free radicals. These radicals immediately combine to form complex organic molecules.
Even at minus 440 degrees.
Through this exact process, even in the absolute freezing vacuum of space, these clouds are synthesizing molecules like methanol, ethanol, dimethyl ether, and formamide.
Formamide. Wait, those are the precursors. Those are the literal chemical building blocks of amino acids.
Exactly. They are the foundation of prebiotic chemistry. These giant molecular clouds are pre-baking the ingredients for life long before a planet ever even exists.
That is profound.
When the cloud eventually collapses to form a star, a swirling disk of leftover gas and dust forms around the new sun. That protoplanetary disk eventually clumps together to form planets, and it brings those pre-baked, complex organic molecules with it.
Delivering them directly to the surface of the new world.
Precisely.
So the alcohol, the sugars, the building blocks of RNA, they aren't forged on the warm surface of a planet. They're forged in the freezing, violent dark of the molecular cloud. And LMA can see these molecules.
It can. LMA has been revolutionary for local astrochemistry. It has detected dozens of complex organic molecules in giant molecular clouds inside our own Milky Way.
So what's next?
The next great frontier, the bleeding edge of this science, is extragalactic chemistry.
Taking LMA and pointing it at the 12,285 clouds in NGC 1387 and looking for the building blocks of life 60 million light-years away.
Precisely. We want to know how the chemical makeup of these clouds varies across different galactic environments. Does a molecular cloud located near the violent, radiation-heavy center of a barred spiral galaxy produce more or fewer complex organics than a quiet, isolated cloud floating out in the outer disk?
That's a huge question.
Are certain regions of a galaxy chemically more suited to eventually harboring biological life? Mapping the extragalactic distribution of comms is the next major step in understanding our place in the universe.
And as we look to the future, ALMA isn't going to be operating in a vacuum anymore. We are currently entering the golden age of observational astronomy because ALMA now has the ultimate tag team partner sitting out in space.
You are referring to the James Webb Space Telescope, JWST.
Yes, JWST. The synergy between LMA and JWST is poised to completely revolutionize our understanding of star formation physics over the next decade.
It absolutely is.
Let's explicitly lay out why they are such a perfect pairing. Because they look at completely different things, right?
They are completely complementary precisely because they operate in totally different realms of the electromagnetic spectrum.
Let's review. ALMA does millimeter waves.
Right. As we've discussed extensively, ALMA operates in the millimeter and submillimeter wavelengths. It is the undisputed master of mapping the cold gas. It sees the invisible hydrogen via the carbon monoxide dye.
It maps the kinematics, the turbulence, the filamentary rivers.
Exactly. LMA shows us the raw ingredients and the mixing bowl of the giant molecular cloud before and during the collapse.
But JWST is an infrared telescope. It looks for heat.
Yes. JWST is specifically designed to capture infrared radiation. While ALMA is mapping the freezing cold gas on the outside, JWST can peer right through the dense, opaque dust of the core to see the heat of the warm, glowing objects buried deep inside.
So you point them at the exact same spot.
Exactly. So LMA can look at a specific core in NGC 1387 and tell us exactly how fast the cold gas is collapsing inward. Simultaneously, JWST can look at the exact same coordinates and image the brightly glowing emerging protostar that is just igniting in the center.
Wow.
LMA maps the gas falling in, and JWST maps the radiation and stellar winds pushing the gas back out.
It's like LMA shows us the dough being kneaded, and JWST peers into the oven to show us the final baked cake as it rises. Together, they provide astronomers with a near-complete, end-to-end, high-resolution picture of the entire cosmic assembly line.
It truly is a golden age. When we pull all these disparate threads together, the fractal power laws, the supersonic turbulence, the inefficient stellar feedback, the chemistry on the dust grains, the galactic recycling, the resulting perspective is just profoundly humbling.
Humbling is the right word.
Giant molecular clouds are not just inert, cold voids sitting in the background of the universe. They are the vital, churning, dynamic laboratories of the cosmos. Every single heavy element forged in the nuclear furnaces of dying stars billions of years ago eventually finds its way into the dark belly of a giant molecular cloud.
To be reused.
Yes. The cloud gathers those elements, compresses them through a chaotic network of supersonic shock waves, laces them with the chemical precursors to life, and recycles them into new suns and new planetary systems.
It is the great billion-year engine of cosmic evolution. If you are listening to this right now, I genuinely hope that the next time you walk outside and look up at the stars, the sky looks completely different to you.
I hope so, too.
Because we, as a species, now possess the sheer technological audacity to build a robotic, supercomputing eye on top of a freezing desert mountain, peer 60 million light years across the void, and map out the exact violent machinery that builds the universe. We can literally catalog the wombs of the next generation of stars.
It's an incredible achievement.
But I want to leave you with one final, deeply personal thought to turn over in your mind. If it is true that these massive dark clouds are the great recyclers of the cosmos, if every single heavy element in your body right now, the iron carrying oxygen in your blood, the calcium fortifying your bones, the carbon that makes up your very DNA was once gathered up, frozen and churned through the violent, turbulent heart of a giant molecular cloud, exactly like the 12,285 we just mapped in NGC 1387.
We are part of that cycle.
Then aren't we, as conscious beings building city-sized telescopes to look back at the stars, simply the universe's way of finally turning around to look at its own birthplaces? We are the stardust looking back at the factory. And if that is the case, it begs a really fascinating question. What might an astronomer sitting on a rocky planet 60 million light years away in Fornax, pointing their own version of LMA directly at the Milky Way, be seeing in our clouds right now?